Hello students, welcome to the world of chemistry. This is Dr. Vikram Panchal and this is lecture number 11 for chemical kinetics. In previous lecture I explained you the units of rate constant K, and from that we can find out order of reaction. Suppose any reaction is given to you, like reactant gives product. Reactant give product. Okay, this is a common reaction. And now if you write differential rate law of this reaction, then we can write minus dr by dt is equal to K, that is rate constant, into concentration of reactant raised to X, where this is known as initial rate of reaction. Okay, so we can find out initial rate of reaction, while this is called initial concentration of reactant, and K is rate constant, X is order of reaction. So from differential rate law, what we can find out? We can find out initial rate of reaction, as we know initial concentration of reactant. So we can find out only initial rate of reaction. That's it. Because we know initial concentration of the reactant. But if we want to find out how much time required to complete the reaction, how much time required to complete 50% of the reaction, how much time required to complete the 70% of the reaction, or in particular amount of time, how much reactant left, how much product formed, all these questions cannot be answered by differential rate law. And for that, we should go with integrated rate law. So from integrated rate law, we got all informations regarding reactions, that how much reaction is completed in particular time, or how much time required to complete the particular amount of the reactions, anything. Okay, so integrated rate law is more important than differential rate law. Now integrated rate law for first order reaction. So for this, we take the same reaction where X is equal to 1. So when we take X equal to 1, it becomes first order reaction. So we write minus dr by dt is equal to K into concentration of R, because X is equal to 1, so we write K into R. Now we change the side of dt and R, so we can write minus dr by concentration of R is equal to K into dt. Okay, on integrating this equation, we get ln R, integration of dr by R is ln R, negative sign can be written on the right hand side, so minus kt plus C. This is equation 1, and where C is known as integration constant. So C is called integration constant, and to find out value of C, we have to consider initial condition. Okay, so for initial condition, in that case, when T is equal to 0, concentration of R is considered as initial concentration, so R0, this become initial concentration. Okay, and for that we put ln R0 is equal to minus k into value of t is 0 plus c. Therefore, c becomes ln R0. Okay, because k into 0 will be 0. So c is equal to ln R0. Substitute value of c, value of integration constant c in the or equation 1, so that we write ln R is equal to minus kt plus ln R0, means initial concentration. Okay, so ln R0 is initial concentration and R is concentration at time t. Now we change the side of kt and ln R. Therefore, we will get kt is equal to ln R0 minus ln R. Or we make it more simple, then k is equal to 1 upon t ln R0 initial concentration of reactant upon R concentration of reactant at time t. Okay, now ln is converted into natural log, so we can write k is equal to 2.303 upon t log R0 upon R, and this equation is known as integration rate law for first order. Okay, there are various forms of the same equation. We write like this also, like k is equal to 2.303 upon t log C0 upon C, where C0 is initial concentration and C is concentration at time t. Okay, or K is equal to 2.303 upon T log small a upon A minus X. Small a will be initial moles or initial concentration, and A minus X will be concentration of reactant at time t. Okay, and the same equation is used for nuclear reactions, and for nuclear reaction instead of k we write lambda. So lambda is equal to 2.303 upon t log n0 upon n, where n0 is initial rate of disintegration of radioactive element and n is rate of disintegration at time t. Okay, because in disintegration of radioactive element, that is emission of alpha beta gamma from radioactive element, is first order reaction. Therefore we can use this equation for the same one, and from this we can find out T. C is the concentration of reactant at time T. Okay, so if you want to find out T, then you should know C. And C0 and K are known. So if you want to find out C, then you should know T, K and C0. So this way we can find out how much time required to complete the reaction, particular amount of reaction, or in particular amount of time how much reactant is left over. Okay, from the same equation we can derive one more equation for half-life period. Okay, so for half-life period, for first order, well, half-life period means how much time required to complete 50% of the reaction. So here we have integration rate law, K is equal to 2.303 upon T log C0 upon C. You can write anything over here. Okay, when T is equal to half, T half means for 50% of the reaction completion or 50% completion of the reaction. then R will be half of initial concentration. So when half of initial concentration is being used, the time will be T half. Okay. So substitute these values in the above equation. So we get K is equal to 2.303 upon T half log C0 upon C0 by 2. Okay, so because R is equal to C, then for it is C0 by 2 also. Okay, and therefore K is equal to 2.303 upon T half log 2, and log 2 is 0.301. Okay, therefore T half will be 2.303 into 0.301, that is log 2 upon K, and therefore we write T half is equal to 0.693 upon K. Okay, so this is also a formula used to find out half-life period for first order. Okay, so we got two formulas. Okay, now we can draw a graph for first order reaction. So a graph for first order reaction would be like this. And here on y-axis we will take log C or log R, and x-axis t, time. Okay, here the graph will be like this. Okay, and this is interception, which we call log C0, initial concentration, and it will be slope. So A, B, C, and therefore slope is equal to AB upon BC. Okay, and that is equal to K upon 2.303 minus K upon 2.303, and therefore K is equal to 2.303 into minus AB upon BC. So this way, if you know slope, you can find out rate constant K. Okay, so this is all about the first order reaction integration rate law. Thank you so much.